So this next skill that we're about to, familiarize ourselves with is almost more of a point of view than anything. And the idea here is because, frankly, we've seen expressions with equal signs. We've seen equations that are not explicitly stated, and we've taken derivatives of such things. We've used implicit techniques to pull it off. But something sort of interesting is going to come into play here, because rather than in the past, when the implicitly stated equations only would have involved x and y, and we would have been able to get a derivative relationship between x and y, you can see in the examples that I have sort of after this first one with only x and y, here we have more variables than just two. So here we've got a, b, c, here a v, an r, an h, here a theta, a y, and an x. And the idea in terms of how we're going to bring calculus into play here is that we are going to think about every variable below as being a function of t. And in your mind's eye, think of t as time. So what you're going to imagine x is something that varies, and in particular, something that varies with respect to time. Imagine that y also is something that varies and is varying with respect to time. Imagine every letter that is written here on the board is something that is changing with respect to time. And the idea here is then, when you think of your x is not just x, but it's some function of time. Whatever function that is, but it's just some function of time. But the thought here is, no matter what function of time it is, whenever you take the derivative of the x, as you know, could be said as like, dx, and over here your dt's. But at the end of the day, whenever you produce the derivative, specifically in this case here, the derivative would be f prime of t. The idea is, if you think of every variable on this board as a function of time, when you take its derivative, the derivative is going to be with respect to time. So let's approach this guy here, because you know this is an implicit equation, and you know anytime you have an implicit equation, we're going to use our implicit techniques to approach it. So when we take a derivative with respect to x, dx, when we take a derivative with respect to y, dy. So this is going to be what? 2x dx plus 2y dy equals 0. Derivative of a constant is just 0. But now, the thing to think about is we're not trying to find a derivative of dy over dx. We're not trying to think of these x's and y's, these letters, as related to each other. We're thinking of them as both related to time. So we want not dx over dy, dy over dx, no, we want dx over dt. And just as well, we're going to be looking for dy over dt. So if you think about this, how are we possibly going to get the dt's into the game? Well, every term here, when we took derivative, had a d something tacked onto it. But what we want is a dt downstairs. But, I claim we can do that, because all we have to do is just take this equation, equal things on both sides. You could do the same thing to both sides, and you'd still have equal things. Well, in particular, you could just divide by dt. And think about this. If you just divide everything in this expression by dt, you'll get 2x dx divided by dt plus 2y dy divided by dt equals 0. And the long story short is, for our purposes at this point, let's just call this a complete expression of our original equation, not in terms of the original functions with respect to time, but now in terms of their derivatives. Take a look at this a squared plus b squared equals c squared thing. Think of each of these variables with respect to time. Well, you know, because this is implicitly stated, you could take the derivative and you'd get 2a dA plus 2b dB equals 2c dc. But now, if we think of each of these variables with respect to time, then all we've got to do is divide by dt. now we've got an expression with respect to calculus. In effect, every dA that we tack on is going to be thought of with respect to time. The dB tacked on with respect to time. The dC tacked on with respect to time. Why? Because we're thinking of our functions with respect to time. What about this guy here? Well, left-hand side, 1 dV dt, no sweat. Right-hand side, product rule, a little bit of sweat, but so be it. You know how to deal with the product rule. What is it? U prime V plus UV prime. Let's just go through the product rule process. Derivative of the first, that's going to be 2 pi r. Carbon copy of the second, that's going to be h. We took a derivative with respect to r, so we're going to tack on a dr, but this dr is with respect to time, so it's a dr dt. Next, u v prime, a carbon copy of u, that's pi r squared. Take the derivative of v, that's the derivative of h, which is 1, but that was with respect to h, the derivative, so this is going to be dh dt. And if we simplify this one down, what, dv over dt equals 2 pi r h, dr over dt plus pi r squared, dh over dt. All right, cool. So here is, for all intents and purposes, a statement related to our original equation, but whereas our original equation is in terms of the original functions v, r, and h, which are changing with respect to time, here now is a statement about the change of v with respect to time, and the change of r with respect to time, and the change of h with respect to time. What about this last guy here? Can we take his derivative? Sure. This is just an implicit expression, so you could use your implicit techniques. Derivative of tangent, secant squared. But now, we took a derivative with respect to theta, so we tack on a d theta, but this theta was changing with respect to time, so we further divide by dt. Now the y over x, that is going to use the product rule, so we're going to need u prime v minus uv prime over v squared, standard product rule stuff. U prime, that's going to be 1, v is x, that derivative was with respect to y, so tack on a dy dt. Minus u, that's going to be y, times v prime, that's going to be 1 dx dt, because we took a derivative of x where x was itself a function with respect to time, and v squared, that's just the x squared downstairs. But the long story short is now here is an expression that relates to the rate of change of our theta, our y, and our x with respect to time. So while in the standard implicit derivative case, we were thinking of dy and dx related to one another, if we loosen our thinking a little bit and just instead imagine each of the variables changing with respect to time, you can come up with expressions related to the change of those variables with respect to time. And well, we'll see, I suppose, in due time just how valuable that can be for us.